Hello students, welcome back. Let's resume section 4. Additional examples. We talked about binomial and Poisson approximation of binomial. Now let's go to hypergeometric distribution, and this one corresponds to an own model without replacement. So binomial was for with replacement, hypergeometric without replacement. And then as a matter of fact, this should be K. Okay, all right, sorry about the typo. So the probability of getting K blue balls out of let's see, some blue balls success with probability, let's see, how many blue balls are there? M blue balls out of total N. So success probability is M over N initially, but without replacement. So it'll go down, down, down. M minus 1 over N minus 1. M minus 2 over N minus 2, like this. It'll go down, down, down. And then probability to get K blue balls is going to be this, because you see there are total M blue balls anyway, so you cannot exceed more blue balls than there is already. So K has to be less than or equal to capital M, and certainly less than or equal to a number of total balls I draw from. So minimum of NOM is the upper bound, and the maximum is, of course, I'm drawing something, so non-negative, so 0 or these. So number of non-blue, N minus number of non-blue. Okay, if that becomes somehow negative, then you have to get from 0. So that's why this bound is there, so that this problem makes sense. Otherwise, you can simply use this, because if you encounter a problem, it must have been well made. So here we go. And the variance and standard deviation formula go kind of like this. N times P, that makes sense. And then variance is, NP1 minus P is similar to what you saw for binomial, but there is some adjustment made. Is there any proof for that? Okay, here we go. If you can follow, be my guest. Otherwise, I'll just show you and just move on. So basically it's this, M over N, and dropping down, dropping down, dropping down. And then failure, dropping down, dropping down, dropping down. We get all those dropping down because we have, conditional probabilities from that point down. They are not independent anymore. And then we can consider rearrangements, because no matter what order we have, in the end, the probability is same, because the multiplication is commutative. You see, if you look at only the denominator, then you get dropping down, dropping down, dropping down from capital N. And if you look at the numerator, dropping down from capital M versus dropping down from capital N minus capital M, either way, it's the same probability. So all you have to do is multiply by the number of arrangements and choose K, which is common for binomial. And then some further simplification, some manipulation, and eventually it is possible to prove that you can rearrange those in terms of binomial expressions like this. Tedious, but it turns out to be true. So I'll just move on. And then as for variance and standard deviation, we couldn't even prove variance formula for binomial because it required multivariable calculus. So certainly we can't do it for hypergeometric. So we're not going to talk about it. How about an example problem here? An urn contains 50 red balls, 30 green balls, and 20 blue balls. Choose 7 balls with without replacement. And the probability you get exactly 5 blue balls, at most 5 blue balls, you can calculate using this formula here for probability mass function, you're selecting 7 balls, so small n is 7, and then how many balls are there total? So capital N is 100, and then capital M is 20 blue balls. So from here you can calculate everything. You see, just this computation, and simplify, and run your computation like this. You can use direct counting techniques as well. So 5 blue balls from the pool of 20, 2 other balls from pool of 80. So from 20, I'm dropping down 5 times. And here from 80, I'm dropping down and then dropping down. And the 7 balls dropping down from 100. And that's what we have here. Blue dropping down from 20, and then this one is total, and then this one non-blue, and then the number of arrangements. Either way, you're going to get the same thing. So you have to do same computation 6 times and add them up. Good luck. I didn't bother doing this computation because it was too tedious. Okay, so much for hypergeometric. Next, negative binomial. This one is a little bit more important, but still, well, it's just additional examples. What can I say? Now, binomial distribution applies to an earned model, finite number of selections, fixed number of repetitions to begin with. Negative binomial is unlimited total selections with target. Suppose that the probability to select blue ball is given as P, and then we are considering with replacement. And we repeat selection until we get total of R blue balls. So previously we had N selections fixed, but here we just repeat until we get total R blue balls. So theoretically, N can go infinitely many. So negative binomial distribution, as a matter of fact, is going to be a discrete but infinite random variable. And then the probability of failures, yeah, okay, all right. So basically it's this: R successes and K failures until you get total whatever. And K can go on forever, at least theoretically. And K plus R trials is where it's coming to an end. And then, let's see, up to K plus R minus 1 trials, you can consider all kind of arrangement, but it'll come to an end. That's the last draw, K plus R trials, right? So the last one must be successed, so that total R success is achieved at K plus R, so that game over. So we're heading something like this: whatever, but in the end, success. So the individual probability is P to the R power, 1 minus P to the K power, like this. And then how many arrangements are there? Well, this is fixed. So instead of K plus R boxes, we have K plus R minus 1 boxes. And among those, if I select not R, but R minus 1 slot for success, the others will be all failures. You see, you have to have R successes, but 1 is taken. So R minus 1 successes out of K plus R minus 1. So that's the arrangement we have. That's where we're getting this. And then it turns out expected value and variance are like this. And of course, this is just formulae. We couldn't even prove these for binomial because that required multivariable calculus. We certainly cannot do this. We'll just accept those. Now, how about an example problem? it is known that a human male probability, human male birth probability is about 0.512, a little bit higher than female actually. Suppose that a couple wishes to have 2 daughters, and they will have children until the second daughter is born. Theoretical example, of course. What is the probability that a family has k male children in general? So it's gonna be this hypergeometric, this one. P-value is given as 0.512 and r power, and 1 minus p, that's for daughters, 0.488 to the k power, and then k plus 2 daughters, so 2, so that's it. See, from here, r value is 2 daughters, and then 2 successes, and then k failures. So for daughter, 0.488, that's success probability. For male, for sons, 0.512, that's failure probability. It sounds a bit awkward to call success versus failure for human birth, because both are supposed to be considered as success. But anyway, it's just mathematical term, okay? All right. In any case, any kind of birth is actually a success for humans. But anyway, here we have that computation. What is the probability that family gets 4 children in the end? So special case, k is equal to 2. So 2 plus 2 is 4. So in that computation, k value is 2. Here, in this computation, k value is 2. Yeah, in this computation here, in the end, k is 2. So we have this computation. And then how many male children would you expect this family to have? So expected value. So expected value here. It's going to be r 1 minus p over p. And then p is the probability 0.488. And 1 minus p is 0.512. And then r is, well, 2 daughters, so r value is 2. So it's this computation. Let's see, I'd like to have this in same viewing window. Okay, this one, r1 minus p over p, and p value is 0.488 for daughters, and then 2 daughters, and then that's complement, that's for sons. Calculate, you're going to get about 2.01. The expected number of total children is therefore 2 plus for daughters, 2 plus 01 for sons, so 4 plus 01. Okay, so much for other examples, and that completes additional examples as well.